Good evening, my fellow mathematicians. This is Chance here, about to prove theorem 51 for you. After numerous attempts of trial and failure, I think I finally have something. So without further ado, we'll be proving theorem 51. Theorem 51 states that the absolute value of the integral from a to b of f is less than or equal to the integral of the absolute value from a to b of f, of the absolute value of f. So proof. Let f be Riemann integrable. That is, the lower Riemann integral equals the upper Riemann integral for f equals the Riemann integral for f by definition 45. By definition 44, let P be any partition, and the greatest least bound of the upper Riemann sum of f equals the upper Riemann integral of f. So we're just going to substitute the greatest least bound of the upper Riemann sum of f for that, which is also subbing for that too. Okay, and now, here we go. Subproof 1 states that a is less than or equal to the absolute value of a, which isn't really a subproof, though it's kind of given. So we'll just skip that. So we have our sum of we have our upper Riemann sum right there, which is less than our absolute value of the upper Riemann sum, which is saying a is less than or equal to the absolute value of a, and that's less than or equal to, not less than, my bad. And then by the triangle inequality, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So, by repeating the triangle inequality over and over and over again for all of n, we get the absolute value of the upper Riemann sum of f is less than or equal to the upper Riemann sum of the absolute value of f, which is just the absolute, which is just taking the absolute value of, like, this is an element, like what all of these as y sub 1 would be an element, y sub 2 would be an element, and just taking all of the absolute values of those, and that would be greater than that by the triangle inequality. So we get this nice little inequality right here, which is the upper Riemann sums of f is less than or equal to the absolute value of them, which is less than or equal to the upper Riemann sums of the absolute value of f. And now we shall get to the proving part. Consider the greatest least bound of the upper Riemann sums of f. If the greatest least bounds of the upper Riemann sums of f with partition P is less than 0, then the greatest least bounds of the upper Riemann sum of the absolute value of f is greater than or equal to 0. The reason being because the greatest least bound, the two greatest least bounds aren't necessarily the same. Because if we take the smallest number and then put it at an absolute value, and then you have 0 in your function, then 0 would automatically become the greatest least bound because the absolute value of 0 is 0, which is less than anything negative that you take the absolute value of. So the greatest least bound in this case is less than the greatest least bound of the absolute value of f. If the greatest least bound of the upper Riemann sums of f is greater than or equal to 0, then the greatest least bound of the upper Riemann sums of the absolute value of f is equal to the greatest least bounds of f. And since that covers all cases, the greatest least bound of the upper Riemann sum of f is less than or equal to the greatest least bound of the upper Riemann sums of the absolute value of f. So using definition 45 and 44 again, we get this right here, which is just saying that the Riemann integral of f is less than or equal to the Riemann integral of the absolute value of f. And now for subproof 2. which which isn't really a subproof though. It's if A is less than B, then negative A is greater than or equal to negative B. So the inequality just swaps. So, taking that in mind, right? We can also infer that the negative of the absolute value of f in this integral is less than negative integral of f, right? And because we have both of those inequalities, we get the absolute value of the integral from a to b of f is less than or equal to the absolute value of the integral of from a to b of the absolute value of f. And since everything in this is already positive, we can just get rid of those, which is equal to this right here. Therefore, proving theorem 51. Have a good night, guys.